Hello all, this is Lakshmi Narayanan. Today we are going to discuss one of the key topics in the field of statistics, which is the least square method. So I'm pretty sure you must have read about time series analysis, which is part of your curriculum. So when you were studying time series analysis, what would have been taught to you is that any time series data will have four components. One is the trend, then you have cyclical factor, then you have seasonal factors, then of course the last one is the random factor, right? So the first aspect of a time series, which is the trend. So it is quite important that while you are analyzing any time series data, you have to understand the trend of the time series data. So it not only helps you to interpret the data that is given to you, but it will also help you in predicting the future of the data set. That is, you will be able to make projections of the future values. Now, when we talk about trend analysis, right? So there are different ways in which, or probably you would have studied different methodologies of studying the trend of a particular data. So you would have done a moving average, uh, probably a mid section average, and the last method, which generally would have been prescribed, is the least square method. There is also uh, one particular thing that is called as a freehand sketch, right? So which is a very primitive method. So barring aside that, from a mathematical point of view, there are moving average and semi averages and the least square method. Now, today we will be focusing on this least square method. We will understand why it is used and how does it supersedes or probably fares better compared to the other methods of trend analysis. Now, you would have solved trend analysis, or probably you would have studied the trend of a data set using moving averages, and you would have observed one thing is that there are specific voids of data when you try to analyze the trend using a moving average. So if it's a 3 point moving average or a 4 year moving average data, you try to analyze, there will be certain pockets of data at the end wherein you will not be able to find out what is the value. So that's where the least square method is better compared to the other types of trend analysis. Now, let's get into understanding what a least square method is with an example. So, let's say we have historical sales data of a company, and to help, and let's assume that the company, or probably today where we stand, is to the year 2010. Now we have a historical data of the company, last 5 years of its sales data. So the company is interested in analyzing the trend of the data, and the second objective is to find out projections for its sales data. So any company in this world, or probably there are different fields of statistics where the interest is towards finding out or projecting your future, or probably projecting future values based on the historical values. So let's start with this example, and this is how your company sales data is for the year 2005 to 2010. Now, just by looking at this data, what do you think of the trend, right? The trend, or in a simple word, I could say that the trend is ever increasing. The sales value is ever increasing, except for the year of 2009, where there has been a dip in the sales value. But on, if I have to look at the data as a whole, one could easily say that the sales value has been increasing. So there is a trend of increasing data set, but Something like this is very vague for a mathematician or a statistician, right? So the idea is to represent it in some form of equations, which will kind of help not only in understanding the trend of the given data, but also in predicting the future values. So the objective, or probably what the company wants, is to predict the trend of future data basis the past data that is given. So the past data is something which has been recorded. Now future is something basis this trend you need to predict. So what do we do? So our objective in hand is to find an equation. So generally mathematics is always related, or probably is always has a base with an equation. So our objective here is also to find an equation. So what does that objective of this equation is to represent the past data. Now we all know that once we have an equation, we can play around by substituting numbers of our interest, and we can get an output value. So if I have an equation basis the past data, if I enter the future year into that equation will throw me the past, or sorry, the future data of sales. Now, yeah, so idea is that we shall use this equation and predict the future sales values, which is what the company wants. So when I say in equation, right? So equation has several forms. It could be a straight line equation, it could be a quadratic equation, it could be a polynomial equation, right? So once you get into this field, what you will see is that you will be more focusing on polynomial and quadratic, because nowadays everything is computerized. There are no manual calculations, right? What When you move to a computer, so computers have powerful processors which can obviously solve multivariable equations. So when you move from solving a problem on pen and paper or using a calculator to a computer, you can certainly look at option 2 or even option 3, because option 2 and 3 will involve a lot of complex computations. So it is not easy to solve them on a piece of paper using calculators. So the easiest of the three is what? Is a straight line. So our objective is to study a trend of the data and probably find out an closest approximation to a straight line. So what we'll be doing today? So today we will be trying to fit a line which shall represent all these data points to the nearest precision. So we all have studied, right? If you have 2 points, we tend to kind of figure out an equation of straight line. But when there are multiple points, generally it is not possible to fit a single line. So the idea why we are saying to fit a line is that we will be kind of figuring out an equation of a line which will give me values of these points to the closest value as possible. So obviously there are going to be errors between what the line will throw and what the actual sales data is. But I think given that we are trying to predict future and analyze the past data, it is always okay to have a certain amount of error, because generally the real world applications can live with some amount of error in predicting values or probably estimating these values. So now the question comes is, how do we fit the line, right? So I mean, right now let's assume an equation of a line, and let's see if that line equation is actually the best fit for the given data set. So let's assume that my line y, which y in this case is going to be the sales data, sales value, is always equal to 8,500. I mean, why have you assumed such a line, right? It is just for simplicity purpose, understanding the concept. So let's assume that y is 8,500. So irrespective of the year, whether it is 2010, 2011, 12, whatever be it, the sales value has to be 8,500. But you may ask me a question, right? It's quite common sense that that's not the right line. But that's fine. Let's try to see if what is the closest approximation of this line for the given data set. Of course, we all know intuitively that this line is not the right fit for the given data. Okay, so now this is how your the green line shows how the data sets are distributed, your past data of sales, and you have another green line, the darker green, which is actually the line which you have predicted for this particular curve. Now, what we will try and do as a first step is to find out error between the value that the line shows to the actual value basis the past data. So right now I'm not even going into the future data. What I'm trying to see is whether this line represents accurately my past data. So let's compute the error in between the values. So how do you calculate the error? The error is actual sales value for the year minus whatever the value that the line throws. So let's start. So this is how our graph looks like. Now, how do you find out the error? For 2005, the sales value was 7,000. Now your line value is 8,500. So you just subtract the two and that should be your error. Now similarly you do it for 2006, 2007, 2008, 2009, 2010. Let's try and put this in a tabular format for us to understand better. So let's tabulate, right? So this is how the value looks. So on the first two columns are what your exact data is, and your third column is obviously the one that the line that we have assumed as predicted. So now the first the first step is obviously to compute the error between the values predicted by the line and the sales value. So how do you do it? I mean, it's just a pretty simple arithmetic. It's 7,000, which is the sales value, minus the 8,500, which is the value predicted by the line. On subtracting what I get 1,500. So now let's do it for the other data sets for 2006, 7, 8, 9, and 10. And it's pretty straightforward. So we get these values. Now, what do I do with these errors, right? This doesn't tell me exactly whether the errors are acceptable levels or whether this line is the best fit or not. So let's try and find a matrix by which I can tell that whether this line is best fit or not. Simply right now let's assume I will sum up the errors and I will look at the sum value. So let me find out the sum of the errors. So it's pretty simple. What I do is I have the errors for each and individual year. I just add them up and that's the value. That's where the value comes out to be 4,500. So that's how the sum of errors is. So right now what I can say with looking at this 4,500 number, whether this is good, bad, or worse, I don't know. I mean, like, I cannot say anything looking at this 4,500 numbers. There could be some other line which has lesser error, right? So let's try and find out. Now, how do we check? So the best example, the best way is to do is, let's assume another line, right? And let's see what happens with that line. So right now, let me assume some random line. Let's say sales is equal to year into 4.78 plus 10. Now, how do you, this looks quite an arbitrary line, right? How do you know that it has to be taken as a 4.78 times the year plus 10? I'm just throwing a simple example, right? This may even not be the right line, but I have taken an example, or probably I've just intuitively assumed this value of the line, either equation of the line, and I'm trying to see how this line fits the given data set. So you have this light green, which is the actual sales data. Now I have plotted the line by substituting the value of year for 2005, 6, 7, 8, 9, and 10, computed the values and plotted it as a graph. Right? So now again, let's start the whole process again. What you will be doing is computing the errors for each year and then tabulating it and trying to, at the end, you will try to sum up the errors and see how it compares with the earlier line equation. So I think the first two columns are pretty simple. It's the actual data set. Then this is what our value predicted by our curve. So it's quite simple. You have to take the equation of the line. For every year, you need to substitute the year value into the equation, and it will throw out what was the predicted sales value. Now, error is simple. We have already seen it's nothing but sales minus whatever the value predicted by the curve. So you have found out what the errors are and you have summed it up. So now the error here is minus 2135 against a 4500 number which was thrown by the earlier curve. So can you guys tell me whether this error is less than the other error, or is it the least error that is possible? Or how do you compare this minus 2135 with the 4500? What the other line what was the other error in the line y is equal to 8500, or the sales is equal to 8500 line? So it's pretty confusing, right? Obviously, it's quite tough to say whether this line fares better or that line fare better. But of course, you could say that this number on an absolute level is lesser than whatever the error is there on the other line. So if I have to say absolute of error value, which is 2135, and the absolute value of 4500, this line seems to be of the least error compared to the other. So what could one say is that a negative number and a positive number comparison has to be done in an absolute sense. So what we will be doing is, rather than looking at an error value as such, we will be squaring up the errors, because see what happens when you have both negative and positive errors, right? See, probably you may have a line, you may have thought of a line which will have error in both the directions. Like probably the error could be in the magnitude of 10,000 negative for one point and a positive 10,000 on the other side for any other data set. Now, if I add all these, there could be a place where they could become zero, right? Let's hypothetically assume that you have a line which actually has both positive values and negative values on the errors, and when they sum up, it becomes the zero. Is that the best fit line for a given data set? It's not, right? It may not be, right? Because the error magnitudes might be very high for each data set, but when you sum it up, it may be zero. So it is quite intuitive to say that an absolute error value, or probably an error value, and summing it up is not the right approach. So the better approach is to square the error so that you negate the impact of a negative and a positive sign. So everything become positive. So the error values are magnified. So now you can easily tell what is the right fit line. Okay, so to avoid confusion and have a better clarity on which line is the best fit, what we'll end up doing is square the errors. Now I think you understand why we are coming to least square. You understand the terminology of least square, right? So always what we end up doing is we will square up the errors and then sum it up. So let's do it for the first curve, y is equal to 8500, and see how it works. So each value is multiplied by itself for the square, and then you have the values. Now just do it for each one, and then at last what you do is sum them up. Now let's do it, try doing it for the second curve as well. It's pretty simple. So the values will stack up something like this. Now what do you see? This is something about 1,26,000 is the error for the second curve, while for the first curve it is 1,53,000, right? So it's quite now easy to say that second curve is a better fit than the first curve. See, you should be careful in understanding what I'm saying. I'm just saying that curve 2 is a better fit, but I'm not saying that it's the best fit, right? So there could be some other line which could be 4.785 y plus some 50, which could yield a even lower error square, uh, and you can term that to be the best fit line, or probably a better fit line than even the second curve. So going by the process of arbitrarily assuming a line and seeing a best fit, you end up getting infinite possibilities of combinations. So mathematically, there has to be a method which can give you and this best line fit basis the data, and that method is nothing but the least square method. So it's pretty simple, right? So now we have two errors, and we understand that the error square of the errors, and we understand that the least error of squares, sorry, the least square error is the closest approximation to the given data set, because the error is less. So it means that it represents the data sets quite accurately. So, so to find the best fit, what we use is square the errors, and the least value of that is taken as the curve that is giving you the least value is taken as the best fit, or probably the better fit. So that's where the method comes as the least square method. Now we have understood how this method works, or probably the background of this method. Now what we will be trying to understand is how do I arrive at the best fit line without having to go through the process of going through the process of finding out, or probably guessing each and every line, yeah, sorry, or multiple combinations of line equations, and then trying to arrive at the squares of error value. So the first thing is that we shall not derive the formula, but we shall straight away get into the formula that is given by the least square method, and then we will solve a problem that will help us understand the whole concept, as well as help us. I mean, all probably understand the methodology or steps behind solving using this approach. So let's start with the least square method. So we will go through step by step process of how it is done, and the formula will be shown at the last, wherein I'll give you the explanation as well. So let's say you have a data like this. You have for 2005 to 2010, you have sales data, and what the first objective is to fit a line which, to a nearest precision, represents this data more accurately. So what there are a series of steps that you need to follow. So let's methodologically follow the steps. So step one is you need to find out what is the average value of the X data set, which is the years, your X-axis value. So average is pretty simple. You need to add all of them and divide by the number of data sets. So here you have 2005 to 2010, add them up. You have 6 years of data, so divide it by 6, and there you go. So your mid-year data is nothing but 2007.5. Step 2 is to sum up the sales. So sum of sales is nothing but your sum of the y-axis data, and you have 70, 80, 96, 100, 95 and 114. Just sum it up and you have 555. Step 3 is about finding the deviation from your average value which you have computed in step 1, which is 2007.5. Let's give it a terminology as X average, and each and every value of X. So you have 2005 to 2010. Find out what is the deviation of each of this from your average X value. So it's pretty simple. 2005 subtracted from your X average, which is 2007.5, right? So I think the formula is mentioned wrong. It's xi minus x average. So it's minus 2.5, and similarly do it for the rest. So you have minus 2.5, minus 1.5, minus 0.5, 0.5, 1.5 and 2.5. Now find the square of this deviation. So the next step is just find out, square up whatever the deviation values on x-axis that you have got. So xd square. So what you do is each column values multiplied by itself, and then you have the data. Now multiply these deviations with the sales value. That's your step 5. So you do minus 2.5 into 70, minus 1.5 into 80, minus 0.5 into 96, and so on till you're 2.5 into 114. So that is minus 175 minus 120. So these are very simple steps. All you need to do is just multiply these numbers and you have the values. Now the next step is about finding the sum of deviations of these squares, right? So you have xd square, you just sum it up. So xd square is nothing but 6.25 plus 2.25, 0.25, and then lastly it is 6.25, that comes out to 17.5. The step 6 is about finding the sum of xd into yi. So xd you have computed, yi is the sales value. You have done that multiplying each 70 by 2.5 separately in a column xd into yi. Now what you have to do is sum all these values. So you have 134.5. So last step is about finding the equation. So any straight line equation we know, right, has is nothing but we have generally seen in mathematical terms is y is equal to mx plus c represents a straight line equation. So I think m and c are constants, so you can replace them with whatever alphabets you want to. So here let's say y is equal to a plus b into x, b into x. Instead of x we will be using the deviation value, right, xd, which we have computed by finding the average of x values and then subtracting it from individual x values. So that's xd. So y is equal to a plus b into xd. So now we need to know how do we compute a and b. So a is given by a formula of sigma yi by n. So n is the number of data set. In this case, we have data from 2005 to 10, which is 6 years of data. So say n becomes 6, and we know yi 555, right? We have calculated it in our table. B is computed using sum of xd into yi by xd square. So let's see what we do with A. A is 555 by 6, which is 92.5. Then you have B, xd into yi computed at 134.5 divided by 17.5, which is 7.68. Now just put them in the equation. There you go. So you have I is equal to 92.5 plus 7.68 into xd. So your first objective is done, right? You have found the equation, and this equation represents the line, or represents the past data in a more accurate way, or this is the line which will give you the least square of errors. Now how do we predict the future data? Now let's say your company wants to estimate the value of sales for the year 2011 and 12. So for 2011, xi will become 2011. But if you look at the equation closely, what you need is xd. So xd is not computed using x average or xi minus x average. So you have xi is 2011 minus 2007.5, which is equal to 3.5. Substitute in the equation, you know y is equal to 92.5 plus 7.68 times xd. So here xd is 3.5. Now just use your calculators and find the value. So you will be getting a value of 119.38. So the sales value, or the value, it's not the value of the sales, it's the trend value for the year 2011 will be 119.38. Let's do it for year 2012. It's going to be pretty simple and straightforward. You're going to do the steps exactly same again, but just that you will be replacing 2012 instead of 2011. So your xi value becomes 2012. xd is nothing but xi minus x average. So 2012 minus 2007.5, which is 4.5. Substitute in the same equation, 92.5 plus 7.68 times 4.5. So just run these numbers in your calculator and you should have 127.06. So that's how your least square method helps in finding the best fit line as well as in finding out the future value of a given data set. So when I say future value, it is the trend value of the future. So that's it for now. I mean, I'm happy to uh, know if you have liked this course, and in case you want me to cover any other topics, please put that in the comment section below. I'm happy to prepare materials and post them as on need basis. Thank you. Thanks for listening to this video. Have a good day.